We'll solve some problems of increasing complexity. Alright, so let's go ahead and begin. So just a quick reminder of Kirchoff's laws. These are very powerful tools that we can utilize for circuit analysis. And the fundamental principle underlying Kirchoff's laws, and I guess everything in reality really, is that of energy conservation. And we'll get to why that is here in just a second. So let's introduce Kirchoff's voltage law. Kirchoff's voltage law essentially states that the sum of all voltages and voltages around any closed loop within a circuit must equal 0. And that's the algebraic sum of all voltages in any closed path in a circuit equals 0, which means that the polarity or the positive or negative nature of the voltage matters here. To give an example of this, consider a circuit in which we have a resistor here, a resistor here, and let's go ahead and tie that off to ground. We'll call this resistor R1, this resistor R2. And the voltage across this resistor V1 and the voltage across this resistor V2. So what this means is that the algebraic sum, so let's call this V source. So as we sum around this loop, if we move around this loop in a circular fashion, then the sum of all these voltages must be equal to 0. So at some level, V1 plus V2 plus V source, I should call this V source, must equal to 0. Now, one thing that we have to do when applying KVL is assign polarity to the voltage sources, which I've already done here, notated by this minus and this plus here in the source, this plus minus associated with this R1 and R2. The nice thing is that we can just choose a convention and stick with it. If we're wrong, it will come out in the math and it will in some ways correct itself. So as long as we're consistent, it doesn't matter if we label this as plus minus or minus plus. We'll always get the correct answer if we apply this correctly. So applying an algebraic sum, how we might do this is choose a starting point to start our trek around the circuit. I always like to start near a source. It just is easier in my mind to do so. So let's start right here. So as we move around this loop in a clockwise fashion, we first hit a minus sign, meaning that as I'm calculating this algebraic sum, I'll put a minus sign in front of this Vs. So minus Vs, moving around, then we hit V1, but we hit a plus sign first, so we'll put a plus V1, and then we're moving around, then we hit another plus sign for V2. So plus V2, and that must equal 0. Now moving on to Kirchoff's current law, this has a very similar interpretation in that the algebraic sum of all currents at any node in a circuit is equal to 0. So again, this is an algebraic sum, meaning that current direction is going to matter here, and we'll define a node here in 1 second. But all currents entering a node is equal to the currents leaving a particular node. So let's create a circuit here. You might be hearing my cat meowing in the background. You'll hear that a lot in these videos. He's really quite sweet. Okay, so let's add in, close this loop off here, and then let's add in another loop here. Now, tie this off at ground. We'll call this R1, R2, R3, and R4. So a node is the connection point of these three resistors here. And so the sum of all currents, this current moving through resistor 1, I1, this current, I'll label it this way, moving out of this node, I2, and this current entering this node, I3. We'll call this node A for convenience. Now, similar to Kirchoff's voltage laws, we can assign an arbitrary direction to each current. We could have them all leaving the node, we could have them all entering the node, or we could have a mix of both. Again, it doesn't matter. If we guess wrong, the math will correct itself. And we'll see that in an example later on in this lecture. But the currents at node A, so current entering must equal current leaving, so I1 plus I3 is equal to I2. Or another way of casting it, if you like, is I1 minus I2 plus I3 is equal to 0. And with these two very simple laws, we can solve our lion's share of our circuits, and these will also form the basis of more advanced analysis techniques such as node voltage and mesh current analysis. Now, this is all conservation of energy. The fact that the sum of all voltages in a closed path must equal 0, and the algebraic sum of all currents entering nodes must equal to 0, is simply energy conservation in that we can't get out more than what we put in. So let's use KVL to solve for a relatively simple circuit here. All right, so within this circuit we have two loops. We have two dependent sources here. So one thing that I always like to do when I'm solving a circuit is to begin by labeling all of my voltages and my currents. So we've got I0 because in this problem we want to solve for I0. So we'll go ahead and create an I1 moving down here. And check this out, we got a nice current source here, so if we wanted to, we could call this I2, but this is already automatically equal to 6 amps. So that should make our job a little bit easier. Okay, now let's get our voltages. So I might call the voltage across this resistor here V0. The voltage across this resistor here, V1. And with that, I think we're about ready to roll. So one thing that I would like you to do at this point is to pause the video and try solving this circuit for yourself, just applying KVL or KCL. Even if you don't solve it and need a little bit of extra help, that's okay. It's good just to practice just writing all of these out. So go ahead and pause this video. All right, hopefully you've written something down, or maybe have solved a circuit. But when you're solving these circuits, practice is really key here. And as you practice solving them, you begin to develop techniques that you are maybe more or less comfortable with. For me, it's easier to see currents entering nodes than it is to necessarily see voltages across the loop. Your mileage might vary there, so I always like to start with KCL if I can, and that's just a personal preference. You can absolutely start with KVL if you'd like. So first thing let's do is evoke KCL. And what do we notice here? Well, we've got, just by our convention, again, if we were to label all these in different directions, it's okay, it'll all work out in the algebra. But the way I have it written, we have at this node, go ahead and call this node A, we have I0 plus I2 is equaling I1. And luckily for us, because of this dependent source, what this really amounts to is I0 plus 6 amps. I might leave out units here as we go along, is equal to I1. Okay, so we've got now one equation, but two different unknowns, meaning that we need one more equation here. So to get that extra equation, well, let's just turn to KVL. And the sort of path that we'll take here is we'll use KVL. We've already got some currents. So it might seem counterintuitive to then move to looking at voltages, but remember, by Ohm's law, V equals IR, we can relate voltages and currents because we know our individual resistor values. So this will be our way to get one more equation we need to solve this. So we'll use KVL, and like I said, I like to start here at the voltage source, and then I'll loop around in a clockwise direction. Now, again, sometimes you might have problems. You could theoretically do a loop here, but this is kind of a trivial loop because the only voltage that's present here is that of V1, so it doesn't really get us much. But here might prove to be more useful. So let's start here. Again, I'll follow my sign conventions. I've got pluses here, approaching nodes, and a minus here for the source. So starting here, I'll make that loop. I'll hit the 120 volt source. And then we hit a plus sign on the V0. So V0, we hit a plus sign on V1 as we move around our loop, and we've completed our loop. So we set that equal to 0. Now let's go ahead and rearrange some things using Ohm's law, noting that V0 is simply I0 times 10, and 10 is our resistor 1 value. Likewise, V1 is just equal to I1 times 50, where 50 is our second resistor value. Okay? Cool. So let's go ahead and plug this all in by Ohm's law. And that's going to get us, I'm going to go ahead and move the 120 to the other side just to make things a little bit easier. So we have, all right, so we have 10IO plus 50I1 is equal to 120. Okay, check this out. Now we've got two equations, two unknowns, which means that we can solve for this. So let's go ahead and solve for I0 first, since that's what we want to solve for. So we know that I0 is equal to I1 minus 6, and then we'll go ahead and plug that right into here. So we have 10 of I1 minus 6 plus 50 I1 equals 120. Okay, so then let's go ahead and solve this out. So plugging this all together gets us 10 I1 minus 60 plus 50 I1 is equal to 120. Doing a little bit of algebra gets us 60 I1 equals 180. And now, go ahead and move up to here so that you can see with the camera. Now, solving this gets us that I1 is equal to 3 amps. And that must mean that I0 which again is equal to I1 minus 6. That means I0 must equal minus 3 amps. All right, and we've solved it. Okay, so let's move now to a more complicated example. So in this example, we introduce a dependent source. And this dependent source is a current source which is dependent upon another current value. If you haven't seen these before, then they're just diamond shapes, and the expression for this current source is listed right by it. So in this case, this current source is a function of I delta or I triangle, whatever you want to call it, but otherwise looks relatively similar to our other circuit. So again, before we begin, I want you to pause this video. Yeah, go ahead and pause this video and take a crack at this. All right, let's move to a more complicated example. And in this example, we have something interesting in that we've replaced our current source in the other circuit with a dependent current source. And these dependent current sources are sources of current which are dependent upon another value of current. Now, this may seem like sort of a trivial or arbitrary like expression or circuit component, but these actually come into play in modeling more complicated circuits with things like transistors. So they're useful to understand and utilize. Otherwise, this looks very similar to our last example. So what I'd like you to do is go ahead and pause this video and give this circuit a shot. Try writing down some equations. If you get it, great. If not, after you give it a chance, go ahead and unpause and we'll work our way through it. All right, so let's begin as I'd like to do by labeling our voltage values. Oh, I guess I should say that what we want to solve for is V naught or V0, which is right here. So if you want to pause again and try it now that I've actually given you the information, go for it. All right, so let's go ahead and label our currents. So we've got a node here that we can utilize for KCL, which is good. We have I0 moving down here, I delta moving this direction, and we've got this current, which I'll go ahead and call ID as in for a dependent source, and an associated voltage with this, and we'll see that this will be trivial here in a second, but I still like to label it associated voltage here, VD. So a couple of things to keep in mind as we're doing this, that once we know I0, we can get V0 via Ohm's law. So that's going to prove useful here. And then once we know I delta, then we know the value of this dependent current source. Okay. Then we know that the current in the dependent source here, I'll call that ID, we know that right, we know that ID then is a function of I delta. So once we get that, then we can completely characterize this circuit. So we have two really unknown currents. Well, if you look here, you'll say, oh, Brandon, we've got three, but one of these is a dependent current. So we really only have two unknowns here. being I delta and I naught. So we have a closed loop around that we can solve for right in here. So let's go ahead and apply KVL. Notice here that we have a similar issue as the last problem, in that if we try to apply KVL in this small loop, well, then we would end up having a trivial answer, as V naught in this case is equal to VD. So probably not a good loop to use. Alternatively, we could use this whole outside loop if we wanted to, ignoring this branch. That's also a possibility. But for now, I'll just do this closed circuit. So starting here, let's go ahead and label our voltages. So plus, minus, and then plus, minus. As you can see, I've got a convention that I like to use. It doesn't matter as long as you stick with it. So with KVL, we'll hit that 500 volt source first, plus V delta, the voltage associated with this current through this resistor here, plus V naught, and that must equal 0. Okay, then if we employ Ohm's law, then that will leave us with minus 500 plus plugging in IR here gets us 5 I delta, and then again plugging in Ohm's law right here will give us 20 I naught, and again that must be equal to 0. So now we've got one equation, so let's go ahead and get that second equation, and to do that we'll just go ahead and move to KCL, and we'll do that here at node A. So just so that you can see it a bit better, I'll go ahead and move everything up here. So with KCL, we have the sums of currents entering I delta plus ID must be equal to the current leaving I0. Well, we've got a nice substitution that we can make right here, since ID is by definition 5 I delta. So we now have I delta plus 5 I delta is equal to I naught. Cool. So then just simplifying this a little bit, 6 I delta is equal to I0. Okay, so now let's go back to our KVL equation and solve for that other unknown. So we'll have, I'll go ahead and move this 500 again over to the other side, so that we have 5 I delta plus 20 times 6 I delta must be equal to 500. Simplifying this gets us 125 I delta equals 500. Then I delta is equal to 4 amps. Okay, now we just simply have to use Ohm's law, which then will get us V naught is equal to 20 I0, which is equal to 400. Oops, haven't gotten to there yet. Sorry about that. So when we have I delta is equal to 4 amps, well, then we can just go back up to this other equation to find that I naught must be equal to 24 amps. Okay, So then plugging this in here nets us a V naught equal to 480 volts. All right, now let's move on to our most difficult circuit here. So this is a real transistor amplifier circuit that we'll have to solve for. So what we want to do is get an analytic expression for for IB, which I haven't drawn out yet. So IB again is going to be from this node. A little background: transistors are 3-terminal devices with terminals labeled as base, collectors, and emitters, and they can act as voltage or current amplifiers. In this case, it's a bipolar junction transistor. That all will come much later, but this is what we're looking at. Notice here that we've also got a dependent source, and this dependent source will represent the gain in our current amplifier, but for now, we'll simply represent it as a constant beta times IB. So we have IB here. We've got 2 separate voltage sources and labeled currents, as well as what are known as biasing resistors, which are just two resistors in a voltage divider configuration. So there's a lot happening here. If we want to find an expression for IB, we note that there are 6 unknowns. And these are I1, the current through resistor 1, I2, the current through resistor 2, IB, the current through the base, IC, the current through the collector, IE, and these are resistors here, so we have an Ohm's law relationship. Okay, so let's go ahead and apply KCL here against all the against our labeled nodes A, B, and C. So with A, notice how I've drawn these currents. Again, if we get it wrong, the math will work out anyway. So let's just go with what we've written. For some reason, as I do these videos, you'll notice that I like currents entering and leaving. For some reason, that works well with my brain. But we know that at A, so up here, we're going to have ICC entering, and then 2 currents leaving, in this case, I1 plus IC. Likewise, at node B, you're going to have a current entering. In this case, that's going to be I1 is going to be equal to I2 plus IB. Okay. Then at C, what do we have here? We've got a current entering, a current leaving, another current entering. So IE must be equal to IB plus IC. Okay. Now notice here, let's go ahead and exploit the dependent source in that we already know that IC, this current right here, is simply equal to beta IB, and that's just by symmetry, as we know that this current flowing through this path must be the same. So we know that IC is equal to beta IB. Okay, so hopefully that's might help us out here in a little bit. So let's first apply KVL. Okay, KVL. So we don't want to use any loop with this dependent source here, and the reason being that we don't know what the voltage across this particular element is. So we want to avoid that if we can. So we're going to go ahead and use these 2 loops, the outer loop here and this loop right here. So let's begin with this loop here. Again, let's go ahead and label. I like to start at sources, and go ahead and label this as plus minus in terms of polarity. So if we start at the source, we have minus V0 plus, we'll call this V2, minus VE is equal to 0. Go ahead and move this up here, which means that if we apply Ohm's law, then we have minus V0 plus R2I2. I don't know why I switched those, but I did. Plus, minus IE RE must be equal to 0. Okay, so we're starting to crack away. We're starting to accumulate enough equations. And it turns out I think we only need one more equation. So I believe we have 5 unknowns here. So let's go ahead and do this outside loop here. Again, I like to start at sources. So we'll call this loop 1. And then loop 2 we'll do now. So loop 2. It sometimes helps if you take notes when you get to more complicated circuits like this on like what loops or what equations belong to what. So this will be node A, node B, node C. So loop 2, starting at this source here, we'll just move around the circuit. Go ahead and label our resistor there. So we're going to have minus VCC plus, then we hit I1R1, or the voltage across this, but substituted with Ohm's law. Then we're going to go ahead and hit R2 plus I2 R2, and that's it. We complete the loop. It's equal to 0, so we'll call this loop 2. All right, so at this point, I'm afraid we'll have to use math. Okay, so let's just start cranking away and solving for individual current values. Hopefully we can then get down to one of these two node equations and solve for IB. So let's start with the outside loop and solve for I1. So we know that I1 R1 is equal to VCC minus I2 R2. Okay, so that must mean that I1 is equal to VCC minus I2 R2 over R1. Okay, now let's plug this back in. Let's try and get close here and get back to node B, so that we know that I1 is equal to I2 plus IB. So that must mean that VCC minus I2 R2 over R1 must equal I2 plus IB. Okay, so we'll have to take care of this term in order to get IB, and we've got IB popping up in a different node equation. So let's go ahead and solve for I2 in this case. So I2 is then equal to, again, plugging this back into here. I2 then is just VCC minus I2 R2 over, R1, minus IB. Okay. Okay, there's a lot happening here. So now we need to be able to get IE, which we'll have to get from our loop 1 KVL. So let's go ahead and solve for IE. So I'll move that up here. Hopefully you can see this better. So then IE must be equal to, this is getting crazy, so BCC minus I2 R2 times R2 times RE, and that's just from manipulation over R1, and all of this minus VO over RE. Holy cow. Okay, so this is getting quite difficult here. But we only now have to solve for IB. We've got all of the terms that we need here to get IB, which means IC and IE. So then IB is equal to IE minus IC. So plugging all of this in means that we have IB is equal to, remember what IC is? We got this dependent current source relationship, which means that we can just go ahead and plug in minus beta IB plus BCC minus I2 R2 times R2 RE over R1 minus V0 over RE. Okay, so there's one last thing we have to do. We've got an IB dependence here. So if we pull that over to the other side, then we'll have IB times 1 plus beta is equal to all this mess, meaning that finally IB is equal to BCC minus I2 R2 times R2 RE, all of that over R1 minus V0 RE, and then all of this multiplied by 1 over 1 plus beta. Oh boy, okay, we got it, but it took us a while. But notice the power of these tools, that even with more complex circuits like we have here, we're more than able just to apply KVL and KCL and get relatively complicated expressions, but solve this circuit regardless.